Have you ever stopped to think about what makes a modern factory actually work? From a car assembly line to a bottling plant, there's this hidden digital brain behind the scenes, making sure every single move is perfect. Well, today we're going to pull back the curtain on this master of industrial automation, the programmable logic controller, or as everyone calls it, the PLC. So, to really wrap our heads around PLCs, we're going to walk through their whole story. We'll kick things off with the big, messy problem they were invented to solve. Then we'll get into the revolutionary solution itself, peek under the hood to see their anatomy, figure out how they actually think, and finally, we'll see where they're being put to work out in the real world. All right, let's jump in our time machine and head back to the days before the late 1960s. I want you to picture a factory's control system, but instead of a computer, it's this enormous tangled mess of wires and clicking mechanical relays. I mean, a whole wall of them. This was the pre-PLC world, and believe me, the industry was desperate for something better.
And here's why they were so frustrated. With that old relay logic, everything was physically hardwired. That means if you wanted to change even one tiny thing in the process, you had to bring in electricians for a huge, super time-consuming rewiring job. The mechanical parts were always wearing out, and trying to find a problem was a total nightmare of tracing wires. Oh, and collecting data? Forget about it. The bottom line is this: the old way was rigid, expensive, and just plain inflexible.
So, out of all that frustration, a truly revolutionary solution was born. Back in 1968, the idea for the very first programmable controller came to life. The goal was simple, but game-changing: replace those massive relay panels and finally bring the power and flexibility of software right onto the factory floor.
Now, the official NEMA definition here sounds, well, a little dense, doesn't it? Let's just cut through the jargon. All you need to know is this: a PLC is basically a super rugged industrial-strength computer. It's built to survive in really harsh places. Think heat, dust, vibrations. And its entire reason for existing is to replace all that physical wiring with a simple program that's stored in its memory. That's what gives it the power to control machines and processes with incredible flexibility.
And what's amazing is just how fast this tech took off. The very first PLC in 1969 was pretty basic, But look at this. By the mid-80s, we're already seeing them with networking capabilities, talking to SCADA systems. This was a huge leap. It wasn't just about replacing relays anymore. This was about building interconnected, intelligent factories. It was really the first step towards what we now call Industry 4.0.
And the impact on the ground was, well, immediate. That rat's nest of wires? Gone. It was all replaced by software. Suddenly, changing a process was as easy as just uploading a new program. They came with built-in diagnostic tools that made finding problems way faster. And because they used solid-state electronics instead of clunky mechanical relays, they were just so much more reliable.
Okay, so what exactly makes up one of these industrial brains? Let's pop the hood and take a look inside the box. Now, PLCs come in all sorts of shapes and sizes. You've got these little compact ones, and you've got these huge modular racks. But deep down, they all share the same basic guts.
This diagram shows you the main players. You've got the power supply, pretty straightforward, it provides the juice. Then there's the CPU, or processor. That's the brain of the whole operation, making all the decisions. You've got the memory, which is where the program and all the data live. And then, and this is so important, you have the input-output system, or I/O. Think of the I/O as the PLC's senses and hands, connecting it to all the real-world buttons, sensors, and motors.
Let's quickly go over their jobs. The processor is like the conductor of an orchestra, executing the program's instructions one by one. The I/O modules are the really important translators. They protect the brain by taking those high-voltage signals from the factory floor and turning them into low-voltage logic the CPU can actually use, and then they do the reverse for the outputs. The power supply is kind of the unsung hero, making sure everything gets clean, stable power. And the programming device, which used to be a special tool, but now it's usually just a laptop, that's how engineers teach the PLC what to do.
And here's a closer look at a critical part of that I/O system. This little guy, the opto-isolator, is a huge reason why PLCs are so tough. It's really clever. It uses a beam of light to send the signal across a physical air gap. This completely isolates the sensitive, low-voltage CPU from the noisy, high-voltage world of the factory. It's such an elegant and absolutely essential way to protect the brain.
So now we know all the parts, but how do they actually work together? I mean, how does a PLC think? Well, the whole secret is in this continuous, incredibly fast loop called the scan cycle. Okay, so a PLC's entire existence is just this constant four-step loop, and it happens in the blink of an eye. We're talking thousands of times a second.
Step 1. It checks the status of all the inputs. Is that button pressed? Did that sensor just trip? Step 2. It runs through the program logic, based on what it just saw. Step 3. It does a quick self-check, make sure everything's okay. And Step 4. It updates all the outputs, turning on motors, lights, valves, and boom, before you can even process it, the cycle starts right back at the beginning again.
So what does that program actually look like? Well, for the most part, it looks like this. The most common language is called ladder logic, and it was designed specifically to look just like those old hardwired relay schematics. And this was an absolutely brilliant move because it meant electricians and technicians who understood relay wiring could easily switch to programming PLCs without having to get a degree in computer science.
All right, we've talked about the what and the how. Now let's get to the where. We're going to move from the theory to the factory floor and see just how common these devices really are.
You know, the short answer is they're everywhere. Seriously. From manufacturing and machining, to food and beverage plants, to the power grid that keeps our lights on, to mining operations and chemical plants, you name it. If a process is automated, I guarantee you there is an extremely high chance a PLC is the brain behind the whole thing. They are the true workhorses of all modern industry. But of course, not every job needs the same tool. For smaller, simpler machines, an engineer might use what's called a compact PLC. It's got the power supply, the CPU, and a set number of I/O points all baked into one little box. But for big, complex processes, they'll use a modular PLC. This is more like building with Legos. You can mix and match different modules on a rack to build a totally custom controller that you can even expand later on.
When an engineer goes to pick a PLC, it's kind of like a tailor fitting a suit. They have to ask a bunch of questions. How many inputs and outputs do we need? How big and complex is the program going to be? How much memory do we need? How fast does this thing have to run? Does it need to speak a specific industrial language like Modbus or Profibus to talk to other gear? And finally, is it tough enough to actually survive the heat, dust, and vibration where it's going to live?
So, if there's one thing to take away, it's this. The PLC started out as a really simple, clever replacement for those messy old relay panels. But it's evolved into so much more. It's become the networked, data-gathering, high-speed heart of the modern smart factory. It's the unseen but totally essential brain that makes our entire automated world possible.
And that wraps up our explainer, but it leaves us with some really fascinating questions to think about. You know, as Industry 4.0 and AI become a bigger deal, how is the PLC's job going to change? Is the visual style of ladder logic still the best way to go, or are text-based languages the future? And what really makes a special, safety PLC so different from a standard one when people's lives are on the line? It's pretty clear the story of this industrial brain is far from over.